Problem 51 states, Hooke's law describes an ideal spring. Many real springs are better described by the restoring force, which is given to us as negative k times delta s minus q times delta s cubed, where q is a constant. Consider a spring with k equals 250 newtons per meter and q equals 800 newtons per meters cubed. So for part A, they want to know how much work must you do to compress this spring 15 centimeters. Note that by Newton's third law, the work you do on the spring is the negative of the work done by the spring. For part B, they want to know what percent has the cubic term increased. The work over, how much has the cubic term increased the work over what would be needed to compress an ideal spring. They gave us a little hint saying, let the spring lie along the s-axis with the equilibrium position of the end of the spring at s equals 0, then the change in s equals s. So, started out by writing out the variables given to us. We have our k constant, our q constant, and then our starting position is going to be 0 meters, like they gave us in that hint, and final position is going to be 15 centimeters, or 0.15 meters. We know our equation for our restoring force given to us, and the equation that we're going to need to find the work done by the spring is going to be the integral of that spring force. So, and like they said, the work done on the spring is the negative of the work done by the spring. So we're going to take the negative integral of that spring force in order to find the work done. So I've drawn out a little figure here along the s-axis. We have our starting position with the spring at equilibrium here, and then we're compressing it, or we want to compress it 0.15 meters. So along an axis, that'd be negative 0.15 meters as our final position. Note the change in s here, and the force of our spring going in the direction towards equilibrium. So to solve, we want to go back to integrating that equation for the restoring force, and can just plug that in there. Starting or final position 0.15, initial position 0, and then we can solve that here. So we take the integral of this, we know is k times delta s squared over 2 plus q times delta s 4 to the fourth power over 4. We know that's integrated. All right, so we can plug in our numbers now. We have k times that change in s. We have our q times that change in s. And we end up with 2.81 joules plus 0.101 joules, which equals 2.91 joules. So this is how much work we must do to compress the spring 15 centimeters. 2.91 joules. Okay, so for part B, they want to know what percent has the cubic term increased the work over what would be needed to compress the ideal spring. So what is the ideal spring? So Hooke's law says that for the ideal spring, we would use this equation here for the work done by an ideal spring. And if you notice, the 1/2 k times change in initial position squared is actually the same equation that we used right here. So we can just plug in that number there. We know that's the work that would be done by an ideal spring. And by that cubic term, what do they mean? They mean this q times delta s cubed right there. So the answer for that one is that 0.101 joules. So we've already solved for those two, and now we can just divide and times it by 100% to figure out what that percent increase of work is, and that's going to be equal to 3.6%. So this problem reinstates our learning goals for this week of introducing the concepts of work and learning Hooke's law for springs and the new idea of restoring force.